one of the poles, making it unipolar, and focusing it so that it can penetrate into deeper tissue. What we'll be covering in this presentation is the scope, the budget, the Gantt chart, work completed, the challenges, our physical design, our circuit design, and our software and what we have to do next.
For the scope, we have to create a functional prototype based on the patent provided by Hassan. It has 3 parameters that has to be met. It has to have a DC square wave pulse width modulated signal. It has to have an output frequency of 30 Hertz. It has to have an instant rising edge because the direct channel between the nucleus and the cell is regularly negative 70 millivolts, sorry. But with the frequency of 30 Hertz on an instant rising edge, it'll bring it up to negative 90 millivolts. But if it's not an instant rising edge and it's a gradual incline, like a sine wave, the channel will adjust to the frequency change and then there will be no change. Also, the magnetic density of the device has to be 10, 200, or 500 Gauss. These are the ideal values for Gauss, and anything above, in between, or below these won't be as efficient as 10, 200, or 500 Gauss. So far, we've completed a budget, a Gantt chart, a project plan, along with several written assignments. For the device, we've done a 3D AutoCAD design, initial programming, and a control circuit design.
This is our budget. Some materials may be subject to change. We have a large listing of materials that vary from multiple metals to small circuitry. At the moment, we are within our budget pricing, but again, subject to change, that might either go up or go down.
This is our Gantt chart here. The top of it displays what we've done so far, the project plan, the design. We've included the holidays right there. After the holidays, we'll be doing the purchasing and the building, and then I've allotted around 2 months for testing because that's going to be our largest component.
For challenges, the calculations for field density has been a challenge because it's very high-level mathematics. There's many calculations that we have to go through and finalize. For understanding magnetism itself, a lot of us going into the semester, we for the most part had little knowledge coming into electromagnetics and magnetism, but as the semesters progressed and we've done more research on the design, we've understood it more. Also, our electrical equipment design course has a magnetism section that we covered later through the semester, and it's helped us with understanding and comprehending magnetism. For signaling, receiving a square wave is hard because the inductor, its nature doesn't go well with the square wave modulator. For time management, we've all had several assignments throughout this course. We have many classes. It's been hard to schedule some stuff, schedule meetings with the client and with Hassan and with the professors. And for pulse concentration, slide A, this is without the focusing magnet. So it's basically like the bipolar device. It's just going around to the other pole. But with slide B, this is with the focusing magnets at the right specifications, and it has a concentrated pulse going through, and that's what we're trying to get. But with part C, the focusing magnets are too strong, so the concentrated pulse isn't able to emit from the device. And that's not what we want. They're too strong.
All right, now we go into the physical design of the project. So we have many components that are going to be consisting of from the original design as provided from Hassan. This is the, so I'll label the materials and then I'll go into sequence on how they work with each other, all right? So first off, we have the material that goes all the way around all the components. This material is called mu metal. It is a shielding material that blocks magnetic waves. The next material that I'm going to go over is the core and the coiling of the wires. This, when injected with a current, will produce our magnetic waves. Next, we have our focusing magnets. These are, as discussed from Brad, they focus the flux density and, as shown here, emit into a laser format. This is the AutoCAD drawing that I produced from Hassan's original patent. It's fairly similar. The main differences is that there is a lot more material. So instead of just having mu metal, I've added a new material called, that is a iron nickel alloy, which has a higher reduction of magnetic flux that can pass through it, and then the mu metal itself can actually block the rest of the field. So this is the material here that's going to cover everything here. This is the nickel iron alloy. This is the mu metal. Then in here we have a core with our coiled wire. Right here, this is the similar shape that it's going to be. If you can't see it, I'm sorry. I chose a poor spot. It has a small extension to allow the pathing of the flux lines so that the magnetic waves stay constant. Again, we have our magnets. Instead of just the original 6, we now have 12. And there is another material that's inside here called gadolinium. I have a hard time saying it, I'm sorry. This material, what it does is reduces heat within the core here so that it doesn't overheat and melt everything else.
So upon being briefed on the project and being assigned a task of the circuitry design, this is the initial circuitry brainstorming that I had come up with in a block diagram format, being very basic. The microcontroller is the device that we'll be using to initiate the pulse modulating signal on the power source. This will be powered by a 5-volt battery so that the majority, the whole circuit for the microcontroller is optically isolated from the high power circuit we'll be using to energize the inductor. Hassam had clarified that he'd like the device to be plugged into the wall, therefore our power source would be a AC power source. My problem with this is that when we are trying to pulse modulate on an AC signal, we get varying amplitudes, and therefore the signal is not consistent, whereas we want a signal that is more consistent from a DC signal if we pulse modulate on the DC signal. Here we see the varying amplitudes that kind of follow the sine wave amplitude as it goes along, and here is just the constant amplitude. So this is what we are trying to achieve. We want that instant rising edge, and we don't want inconsistent results, which will make it harder for us to actually research and test the device itself. The optical isolator, how that basically works, is an infrared light emitting diode, which, when energized, turns on a transistor, which will be connected to the inductor, which looks a little bit something like this. So a light emitting diode, which is infrared, acting on a transistor. This has no connection. Transistor, that's not a straight line. So current will flow to ground, and this resistive load, in our case being the inductor, will be energized. So that's basically how the optical isolator works in this scenario. This is a testing and simulation circuit design that I prepared in order to help us determine the density of the flux lines within a radius of the core, so we can kind of experiment with the nature of the inductor and get more or less a concept of how it really works when we're trying to apply the DC pulse width modulated signal. In our past courses, like Electrical Principles 2, for example, we have some knowledge of this through theory, but in practical labs, never really dug into how to actually use an inductor in a circuit. So before getting into explaining a bit of the circuit here, I'll explain a little bit how inductors work in their nature. When you have an applied current or any change in current over an inductor, as we see here, current flowing to the right, an expansion of magnetic flux around the coil and the conductor produces a relative motion between the magnetic field and the conductor. This induces a voltage, which is known as counter-electromagnetic force, which opposes the power supply we are injecting into the inductor. This means that it takes a certain amount of time for the inductor to reach maximum ratings. This time is known as the transient time. What is also to be noted about this is that what happens when we shut off the power supply to the inductor? The counter-electromagnetic force is still present. Therefore, there is a power surge the instant that we open the switch to close the circuit, to de-energize the circuit. That means that we have to protect the rest of the circuit from this inductor here. And I've done this using an L293D chip, which we have previous experience using from a microcontroller processing course this semester by Michelle Hambury. Because we have lots of experience with this, I figured it would be the best option to use when going about testing. The main difference between this circuit design and the prototype final design is that the power source is already rectified in DC. We can vary the voltage and current as much as we'd like to, making it very nice for us to test. Also, one other thing to note is that the specs for the L293D specify that the maximum current is 400 milliamps that we can run in the same circuit. So therefore, the current we're limited to on the DC power supply is 400 milliamps. I thought this was very good because we want to be able to use low voltages. We want to be able to experiment with the circuit without worrying to have to protect from high voltages, and just in this case protecting from the inductor. So in regards to transient time, what does this mean for our circuit? The transient time means that if we can't have 50% of the time building up, 50%, I always forget I have this. That we spend 50% of the time building up and 50% of the time decaying, we get a gradual rise and a gradual decrease. Whereas Brad was mentioning before, we want that instant rising edge. And also, if we look at the right here, if we have a build-up time and a decay time that is greater than 50%, we never actually reach the maximum rating, so we don't want that either. So what is optimal for us is to have the build-up time and decay time be less than 50% of the period, which means 50% of the entire pulse, so meaning between here and here. We want that to be less than 50%, so we get more of a rising edge and more of a consistent signal, which is what we want. Curve A curve A and B on the right, and this graph represents current over the inductor. So curve A here represents current over the build-up time. So at the instant that the switch is closed, we start at 0% current, and we eventually rise over to 100% current over 5 time constants. And the inverse happens over decay. So we start at 100% current and over 5 time constants, end up at 0%. So once we get all the transient time testing out of the way, another few ideas once we've actually experimented enough with that circuit is to implement some ideas such as these, which would be having iron powder, which is a ferromagnetic material which will respond to the magnetic flux lines emitted from the core. This way we can actually kind of get a visual of how the flux lines are actually acting around the magnetic material. So as you can see here, the lines from the north pole are going towards the south pole. I say that because magnetic field flux lines are vector quantities and not just scalar quantities, meaning that they have a direction. So we can kind of see that here. And what we would like to use this same principle for the core within a radius, so we can actually kind of see, okay, our efforts actually achieving any results? Are the waves propagating in all directions and losing strength dramatically, or are they propagating in one direction and in a focused manner? The next testing we would like to use for this circuit is using Hall effect sensors. So similar to a Gauss meter, Hall effect sensor runs a small current through the semiconductor material, which is influenced by external magnetic flux lines. So when this happens, electrons move to either side of the slab of the semiconductor material, and in this case, it creates a potential difference known as the Hall voltage, which we can measure. So this will let us, again, get a real idea of where the density of the flux lines are at the most. Are the magnetic field waves propagating in the way we intended or no? These are the questions we'd like to answer.
Okay, so for our initial programming, the main problem with this, is the programming that's built into the Arduino that we're using, the pulse width modulation thing that's built in, only controls the duty cycle. So as Brad mentions, we have to have 30 hertz. The default hertz for the Arduino is 980. So to counteract that, this part of the program right here, I've manually turned the pins on and off to create a wave. So this top part will name the pins. This void setup part right here will make it an output to turn it on, or to make it able to be turned on. This first line turns the pin on. The default delay time for Arduinos is milliseconds, so this will turn it on for 3 milliseconds. Then this will turn it off again, and then this at the bottom will turn it off for 30 milliseconds. This will create the 10% duty cycle that we think we need for the final prototype. So the next slide is same thing, except I've adjusted to the 50% right here, the delay time. So this is mainly for testing. We're going to start at 50% and go down and see what's the optimum way to do it. The next one, I've added a temperature sensor up here. So this will, there's a library, so you upload the library to it up here. And then I've also added an LCD screen. This will initialize the LCD screen. So basically, we turn the signal on right here at the same 10%. Then if the temperature inside the core goes above what we've set, it'll turn the pin off, and it'll display overload on our screen. The next program is the same thing, except it's 50% again. So for what's next, after the break, we have to order the parts. We have to build a simulation circuit, test that circuit, build a prototype, test it, and then can finish the technology report. And any questions?
Thank you.